All right, AP Physics students, welcome. We are about to dive into one of the most famous, and let's be honest, one of the most confusing laws in all of physics. I'm talking about Newton's third law. If you've ever found yourself totally stumped by it, you are definitely not alone. But you're in the right place because today we are going to make it all click once and for all.
So, yeah, physics' biggest paradox. Why do we call it that? Well, because this law presents a puzzle that just seems to fly in the face of common sense. It trips up pretty much everyone at first. It just feels like it can't possibly be true, but of course it is.
And here it is. This is the question that breaks everyone's brain. If every single action has an equal and opposite reaction, then why does anything move at all? I mean, think about it. If you push on something and it pushes back with the exact same force, shouldn't those two forces just, poof, cancel each other out, right? Shouldn't everything just be stuck in place forever? It's a totally logical question to ask, and that is the paradox we're going to crack today.
Okay, so let's get into it. The secret to solving this whole thing, it all comes down to one single, often overlooked detail. I like to call it the different objects secret. Seriously, once you get this one idea, everything else just snaps right into place.
Now, you've all heard the law stated like this. For every action, there is an equal and opposite reaction. It sounds so simple, right? So elegant. But here's the problem. On its own, that definition is completely misleading. In fact, that simple sentence is the entire source of the confusion because it leaves out the single most important part.
All right, this is where we separate the myth from the reality. The common misconception, the one that gets everybody, is that these equal and opposite forces cancel each other out, leading to zero net force and no movement. But the physics reality, well, it's that the forces act on two different objects. And because they're acting on different things, they literally can't cancel each other out. You can only cancel out forces that are acting on the very same body. That's the whole game right there.
So listen up, because this is the key takeaway. If you remember one thing from all of this, let it be this. The forces in an action-reaction pair, they never, ever act on the same object. That's it. That's the secret. That's the entire thing you need to know to solve the paradox.
Okay, enough with the theory. Let's look at some action-reaction pairs out in the real world. Seeing these force pairs in action is going to make this whole thing crystal clear. I promise. Let's start super simple. Imagine you just push on a wall, okay? Force A, the action, is your hand pushing the wall. But what's force B, the reaction? It's the wall pushing back on your hand. See what's happening? One force is on the wall, the other force is on your hand. Two totally different objects. So there's no way they can cancel each other out.
All right, how about walking? This one's a classic. You might think that to walk forward, you push yourself forward. But you don't, not really. The action is actually your foot pushing the ground backward. So what's the reaction? The ground pushes your foot forward. And get this, that push from the ground is what actually moves you. It's the ground that propels you forward. Kind of wild, right?
It's the exact same principle for a rocket blasting off into space. The action is the rocket engine violently shooting hot gas out and down. And the reaction? That stream of hot gas pushes the rocket up. This is why rockets work in the vacuum of space. They aren't pushing against the air or a launch pad. Nope, they are pushing on their own expelled gas, and that gas is pushing right back on them.
Okay, one last example just to drive it home. A swimmer. How do they move? Well, the swimmer's hands push the water backward. That's the action. And in reaction, the water pushes the swimmer's hands and their whole body forward. Do you see the pattern here? In every single one of these cases, you push on the world in one direction and the world pushes back on you in the opposite direction. And that's what causes motion.
Okay, so now we're solving the motion mystery. We've established that the forces act on different objects so they don't cancel. Awesome. But that kind of brings up a new question, doesn't it? If the force the cannon pushes on the cannonball is equal to the force the cannonball pushes back on the cannon, why does the cannonball go flying off at super high speed while the cannon just kind of rolls back a tiny bit? We need to solve this final piece of the puzzle.
And the key to that puzzle is this beautiful idea. The forces are equal, but the accelerations are not. See, to fully get the third law, you actually have to bring in Newton's second law. You know the one, F equals ma. The forces in that action-reaction pair are always equal in size. But the effect of that force, the acceleration it causes, well, that depends entirely on the mass of the object it's acting on. And this table just lays it all out perfectly. Let's look at why the cannon and the cannonball move so differently.
The force on the cannonball from the cannon, let's just call it F. The force on the cannon from the cannonball, also F. They are identical. But now look at the mass. The cannonball's mass is tiny, so when you divide F by that small mass, you get a huge acceleration. Meanwhile, the cannon's mass is enormous, so that exact same force, F, divided by a huge mass, gives you a teeny tiny acceleration. Equal forces, but wildly different outcomes.
All right, let's land the plane here with your final force challenge. We're going to give you a quick cheat sheet to make sure this all sticks, and then I'm going to hit you with one final question to see if you've really got it.
Okay, here it is, your test date cheat sheet. Think of these as the 3 non-negotiable commandments of Newton's third law. Rule number 1, action-reaction forces are always equal and opposite. No ifs, ands, or buts. Rule number 2, they always act on 2 different objects. And rule number 3, because of that second rule, they never, ever, ever cancel each other out. Burn these 3 rules into your brain and you will own any question they throw at you.
And now, for your final challenge, I want you to really think about this one. A tiny little mosquito hits the giant windshield of a speeding truck. The question is simple. Which one feels the bigger force, the mosquito or the truck? Think back to the rules we just covered, especially rule number 1. The answer might not be what your gut tells you. Thanks for joining me on this one.